we were discussing joint distributions. Before that, there was some issue with expectation about linearity and other things. We will sort this out and then continue discussing joint distribution. So if we have a random variable, which is of course just a function from omega to r such that it satisfies some condition, that is something is in the sigma algebra. Okay, that's not we need. Then we defined this x plus, I don't know whether I used x plus or something, but we can define this x plus equal to maximum of 0 and x of. Similarly, x minus equal to x minus x omega equal to maximum of 0 minus x of 3. Okay. Then this having, if x plus omega equal to is not 0, then x minus omega is 0, and x minus omega, this is just the negative part of x, this is just the positive part of x, and one of them is non-zero, the other one is 0. Okay. So, and that can be written as x plus x minus equal to 0, and another one is this x is equal to x plus minus x minus. Okay. Huh? Okay, x plus minus x minus. Okay. Okay. Now we know that modulus of x is equal to modulo x plus x minus. And the claim is E of x is E of x plus, which is positive, E of x minus. Okay. So we have already proved the following: E of x equal to integral 0 to infinity 1 minus f of x dx minus integral minus infinity to x f of 0 f of x dx. Okay, I may, this subscript I may not write all this. This is just to, we have proved this already. And as you can see, this is just integral 0 to infinity probability of x greater than or equal to x, okay, which is same as, I mean, x is positive. Okay, for x is positive, x is in the interval 0 to infinity, x is positive. So x greater than or equal to 0 is same as x plus greater than or equal to x, right? X, I mean, in this interval 0 to infinity, x is in this 0 to infinity, x is positive. So x is greater than or x is same as x plus greater than or that, right? So this is minus whatever we have here. Okay. Now this is equal to, of course, E of x plus. Okay. By our definition, E of x. This is positive. For positive things, we have proved that for positive, this is just E of x. It is just this term. Okay. So we have to prove that. We only need to prove minus something. Only need to prove E x minus equal to integral whatever minus infinity to 0 f of x. That's what we want. So let's compute E of x minus. E of x minus is integral 0 to infinity probability of x minus greater than or equal to x, okay, dx. By whatever we have done. We have done, I mean, we have proved the two things. Ex equal to this, and when x is positive, Ex equal to integral 0 to infinity 1 minus f of x dx, if x is positive. Okay. So because if this x minus is positive random variable, x plus is positive random variable, so this is true. Okay. Okay. So this is same as integral 0 to infinity probability of minus x minus is less than or equal to minus x, okay, which is of course 0 to infinity f of x minus of minus x dx, right? F of minus x minus, minus, wait. Yeah, minus x, minus x minus is, minus x minus is less than or equal to, this is equivalent to saying x is less than or equal to minus x. X is positive, so minus x is negative. Minus x minus is less than that. Minus x minus is equal to x. Okay, when x is negative, when small x is negative, minus x minus is equal to x. That's what this says. Okay, x is equal to, sorry, this x is equal to this. So when x is positive, x is equal to x plus. When, I mean, x in small x is positive, or I mean, when not small x, sorry, forget about that. When this x random variable, wherever it takes positive values, it is equal to x. Negative values, it is there. So minus x minus is less than minus x. It means x is less than minus x. So this is just f of x at minus x dx. To change the variable to minus c, you will get a minus sign, and you will get, I mean, you will get minus infinity 0. This is the same as minus infinity 0 fxx dx. That's what we wanted to prove. Okay? We only wanted to prove here. Is it okay? So it's very simple. We have to do this. Okay? So we proved this. The first term is just the positive part of it. Second term is the negative part of it. Positive part is clear. We use just the definition and then go through this and get this. Okay. Okay. And we had also proved that if g is a function from R to R, such that g of x is a random variable. I mean, for a continuous random variable x, g is a function, possibly, I mean, continuous, it will certainly imply. So it's something, some function such that g of x is also a random variable. Okay. Then we proved that e of g of x, I mean, and g is positive. For positive, we proved this. Okay, g is positive. This is equal to integral 0 to infinity g of x f of x x dx. Okay, this is the density of x. This is our fx is the density of this capital X, and this we have proved. For positive, we have proved. So for a general thing, e of gx, for general g need not be positive. For positive, we have proved. This is equal to e of g of x plus. Okay, then e of g of x minus, okay, whatever it is. But then g of x plus is nothing but g plus of x. Where, I mean, when we have g, we have a g plus for that. G can be decomposed into g plus minus g minus, positive part and negative part. Okay, so g plus x minus e of g minus x. So for this, we have that formula that this is equal to g plus x fxx dx minus integral, of course, whatever, 0 to infinity, 0, whatever. And if you just add those two things, g plus minus g minus, I mean, okay, it is just, yeah, you will get, you just have it minus infinity. I mean, you change it to minus x and all that, you will do the same thing, you have x. Okay. So in general, this is true. Okay. So corollary to all these things, okay, we have a corollary to all these things. We have, if x is linear, ex is linear, x1, x2, two random variables, then e of x1. So before that, I want to generalize this. Sorry. Now we know, but so if I mean, we know that if x1, so let's say define it for general. If x1 up to xn are random variables, these are all okay. You're still looking at it. So I can write. Want to write it? Yeah, fine. Okay. Okay. X1, x2, xn are random variables. Okay. And then we can so this is x1 up to xn is an element of Rn such that inverse image of any square or something, or I mean, it's usually a minus x to infinity. I mean, it just sets like this, minus infinity to x1 cross, something like that. N of them is inverse images in the signal algebra, but that will imply that for any open set square root, I mean, you can prove that inverse image of any reasonable set is in the signal algebra. Okay. Then we have this fx1, we defined fx1 up to xn, up to xn up to xn is equal to probability of xi less than or equal to xi, okay, I between n. So we defined it for 2, for n things we can define. And we say that x1 up to xn, this admits a density if this f of x1 up to xn of this x1 up to xn is equal to integral. I mean, like double integral, you can define n integral. You just integrate with respect to that variable, keeping other variables as constant. That partially integrate. Okay, that's what. Up to x2 up to minus infinity to xn, f of x1 up to xn. So this is, I mean, I have to write x1 up to xn here, but I am not writing. Okay, up to d x1 to dx. Just integrate it n times, n integral, like double integral is n integral. Okay. Okay. This is about, this is, I'm just recalling, we defined all these things for 2, for n equal to 2, I'm just recalling for general n. You just change it, no? I mean, you have to have minus x here, okay? Then if you put minus x here, this will become minus infinity, this will become 0. G? G? This is g minus, okay? You change it to minus x. What's happening? Is there a problem? Minus g minus x. Yeah, inside there is. Wait. G minus x. G minus. Yeah. This will be. Yeah. Yeah. It is just the, yeah. Except for that, right? I hope it's okay. It should be okay. Okay. There should be a problem. You check it out. Okay. Okay. So I want to prove the following. I mean, we can prove it for n equal to 2 if you want. G is a function from Rn to, we have x1 up to xn, random variables. G is from Rn to R, such that G of x1 up to xn is a random variable, whatever it means. Okay? So that this is just a real valued function from the original omega to here. So this is a random variable. Then, provided the expectation exists, I mean, I am not writing those things. Whenever I say something, then E of mod of G of x1, I mean, then if G of, okay, let me write it. G mod of G of x1 up to xn is less than infinity. I should have written there also. Then E of, this also we can calculate using the same formula. Okay? Or I should write it for positive first and then do that. Let's assume G is positive, then it will be the same way it will be true for anything, right? Okay? G is around G, let G be greater than 0. So to 0 infinity. Okay? It's a positive value random variable. We can prove it for positive. Then, I mean, I will prove for positive. Then it will be true in general. Okay? G of x1 up to xn is a random variable. I mean, the same way we can prove it. There is no difference. If G of x is a random variable, then E of, here I don't have to, less than infinity, I don't have to assume. If it is infinity, then that integral will also be. If after positive, there is no confusion. Only when there is negative infinity minus infinity happen, that's a problem. Okay? E of G1 equal to integral 0 to infinity G of, no, wait. Yeah, E of, one second. There is some mistake somewhere. When I say, where did I write G equal to that? This is not 0 to infinity. No? I mean, minus infinity, right? Yeah, all these things are minus infinity. That's because, I mean, x can vary, but huh? Yeah. It's because x can vary everywhere, no? X can vary everywhere. Okay? It is just that G is positive. So for that, I mean, in that proof itself, it goes on like that. It is just the set where it is. So it should be minus infinity to there. It's okay. Okay, we'll go through the same proof again, except for it's for n case. So it will be clear. Okay, we are going to go through that. So it should be minus infinity. Huh? Yeah. Anyway, we'll go through it again. We are going through it again. Okay, this is what I want. G of x1 up to xn is equal to, let's assume just two variables. N1 is, n variable is clear. Okay, xy are random variables. Then, I mean, it's easier to do. Okay, N1, you will have n integrals. That's all. Okay, then G of xy such that G of xy is a random variable. So we have two random variable xy, and G is a function from R2 to 0 infinity. You can assume n if you want, Rn. Then E of G of xy, this is just a real valued one. This is just one dimensional, real valued one. This is equal to integral minus infinity to infinity, minus infinity to infinity. Okay, G of xy. I am assuming positive. G is positive. Okay, G is positive every time. Minus infinity to infinity. G of xy, f of xy, dx dy. Okay, let's prove it. Okay. Okay. G is positive is equal to integral 0 to infinity. Okay. G, I mean, f of G of xy at x. Yeah. Sorry, 1 minus. Okay, by our definition. I mean, this is same as integral 0 to infinity probability of G of xy greater than or equal to x dx. Okay. By our earlier, whatever we have proved from that, this is true. Okay. Now I mean, so I should have said that for any, I mean, this is true in general. If it's in R2 in Rn also, if you have any set B, then probability of x1 up to xn in B, as far as B is a reasonable set. For example, it is just it's generated by rectangles or something, a union of rectangles or something. Then this is equal to R. I mean, countable union of rectangle need not be a rectangle. It can become anything. Then you can take countable union to get circle, whatever. I mean, it's possible to get almost all open sets, everything by doing that. But as far as it's a reasonable set, then this is equal to integral over B. B is R, B in Rn, right? Of f of x1 up to xn dx1. You need not worry about this. What is this B? Because we are going to change. We are going to apply change of variable and we will get something. Okay? So this is same as integral over. I mean, we have only double integral here. Double integral over G of where this set all those xy such that G of xy. I am using. Okay, I use z here. Sorry, I changed to z. Please, because I want to use x and y here. G of xy greater than or equal to z. Then, okay, then f of xy dx dy. Okay. Then integral 0 to infinity dz. Right? Integral over this, I have just replaced this. This is equal to integral over this set of that density f, right? This 0 to infinity, I am just keeping it. Here there is an z. Let me start from that. E of this is this, okay, with the variable z here, with the interval, okay. And this is same as this, of course. Here the integral is 0 to infinity P of G of xy greater than z dz. Okay, the integrating that independent variable is z. Okay, earlier I wrote x, I changed to z because I want to use x and y there. Okay, now this is this probability is just integrating the density function over this set. Okay, that set I have written here. G of xy, these things we have gone through already. Okay, xy such that d of xy greater than or equal to z, f of xy, that is this double integral. Then there is another integral here. This is from 0 to infinity when g is positive. G is positive, so the value will be positive. This is greater than z, that's what we want. G is positive, so this whole value will be positive. So that's what we want. Okay? Okay? Xy will vary everywhere. So this is between minus infinity to infinity. So that's what happening there also. Okay. Okay. Now we interchange this integral, this xy. If you interchange this integral, okay, let me write it and then I will tell you. So this integral here, g of xy is greater than this. So here this is, I mean, this is for x and y, this is for z. Okay, this will be between 0 to g of xy, okay, of dz. Then f of xy. I mean, if you want f of xy, dz, dx, dy. Okay, I have just used this condition. The same thing. Please take a minute and get convinced. If you are not convinced, take a minute and get convinced. Sorry. This is double integral. See, the double integral is always like that. You interchange it. Here there is no problem. If there is something is not included, that will become zero there. That will become one-dimensional or something. So integration will not happen. So I have just, this is minus infinity. I have taken it. But for now, the variable here is z. Okay. Now here 0 to is infinity, it varies, but then it is over this set. This is not, oh no, I have also written and you are also saying here there is no 0 to infinity. I'm sorry. Please. This is 0 to infinity. Then this is over this set. That's all. Okay. Sorry, there is no 0 infinity. Okay, greater than or equal to z. Then f of xy. I mean, this is just double integral. This is just over this set. There is no infinity. Okay, f of xy dx dy. Then there is dz. Okay, now this is okay. This is okay. Now I take these two integral out and take this integral inside. So when I take this integral, this is a general minus infinity to infinity. Okay. When I take this integral, what is where this varies? Here, this varies. G of xy should be greater than 0. So the z will vary between. But then I mean, z is anyway greater than 0. It should vary between 0 to gxy. Okay. Then f of xy, whatever we have, the integrand is this dz, dx, dy. There is no z here, so this will become g of xy to infinity. Yeah, z is positive. Yeah, let z is positive, so it's from 0. It cannot go beyond g of xy. Okay, so now this is equal to minus infinity to infinity, minus infinity to infinity. This is just g of xy, g of xy, f of xy, dx, dy. Okay. Anyway, you have to understand this double integral in the next semester, so please better understand now. Okay. So that's all. This is for positive. So the same way, if g is anything, g goes to real, then also this is the same thing. Okay. We are doing it continuous random. This is for only continuous random. This is true in general. You can mix discrete and continuous also. Then also this is true. But we are not doing it. This one. Yeah. Correct. That's why I don't care about this inequality sign and other thing. Okay. This is in general g of something, whatever. Okay. This is in general. That's an exercise. The same thing. G plus g minus. We just use it. Okay. This is okay. Now corollary to this is E of x1 plus x2 equal to E of x1 plus E of x2. Okay. I mean, what you said, the proof is correct provided we have this. Okay. We need this. Okay. That's all. Okay. Now this is a function. Okay, I mean we have a function g from R2 to R. This is just x1, x2 going to x1 plus x2. This function. Okay, so E of by that Wagner formula we have this is equal to integral of x plus y, maybe x plus y, okay, and f of xy, okay, dx dy, integral minus infinity, infinity minus infinity. Okay. This is equal to integral over x. You just keep x and then minus infinity to infinity, integral minus infinity to infinity f of xy dy. Okay. Similarly, integral minus infinity to infinity y, integral minus infinity to infinity f of xy, I mean dy, then there is dx outside. Okay. F of xy dx, then there is dy outside. Okay. Okay. There is nothing. Is there anything? Is this is if you want, you take this x y going to x plus y. Okay. Okay. This is okay. I'm just applying that theorem to this function. So it has E of x1 plus x2 equal to this. I just have to write this function, right? If you have any function from G from Rn to R, if you want to take the expectation of E of G of x, you just take that function and then integrate multiplying by the density. That's what I'm doing. Okay. So that's what I have here, x plus y, f of xy, the two variable function. So this is same as one, I mean, this x I'm keeping. This is integration is linear. So I integrate this first and then this. Okay. So x integral of the one integral, if I take it inside, minus infinity to infinity. And similarly, I take this. But then this minus infinity, this is just the density of, when you integrate it over y, you get the density of x. Okay. So this is just minus infinity to infinity, x, fx. I haven't written xy, you have to write it. Okay. Fx of x dx. Similarly, minus infinity to infinity, y, fy of y. Okay. I mean, when I integrate between minus infinity to infinity of the two variable density function with respect to y, I will get the density of x. Similarly, if you integrate with respect to x, you get the density of y. So because of that, this is true. So this whole thing implies that this is equal to E of x1 plus E of this is x1, this is x2. I have mixed up. I should have used xy. Doesn't matter. X1 and x2 or xy. Okay. E of x2. Okay. I hope this is fine. Okay. So integration is linear. Okay. Then we define the following. We actually have defined this. We can generalize to n variable. X, Y, two random variables are independent if probability of this set, probability of x less than or equal to x, y less than or equal to y. Okay. Probability of x less than or equal to x and y less than or equal to y is equal to probability of x less than or equal to x, probability of y less than, if it is multiplicative this way. Okay. So this is what is independent is. Independence is. So from this, you can, I mean, this is just saying that probability of this set, right? Minus, I mean, if you use the, I mean, in terms of density, this says that f of xy, this is minus infinity. This is the set corresponding to minus infinity to dx, minus infinity to y. F of xy equal to f of x times f of y. That's what this is. Okay. Okay. That's what this is, right? Okay. So from this, actually, you can write any rectangle. This is just easy manipulation. This says that if you take this thing, I mean, this rectangle goes up to minus infinity. Probability of this set which is equal to minus infinity x cross minus infinity y equal to the product of that. Instead, if you take the rectangle, you do this manipulation. If you take the rectangle, that is going to be big rectangle minus this rectangle minus this rectangle minus this plus this rectangle. This infinite rectangle, it goes to infinite. We have already seen this. Probability of that will be probability of this infinite rectangle and this infinite rectangle minus of that plus this, because you have added this twice, so plus this. Okay, because of that you can write it down using minus infinity x and all that. From all these things we will say that p of ab whatever ab cross b cd. Okay, I mean probability of, okay, let's write it clearly. X and y are independent, so probability of x in AB, okay, y in CD, okay, equal to probability of x in AB, probability of y in C, right? Okay. This is, you don't, doesn't follow immediately. You have to write the whole thing and then you can group out, factorize what's happening. Okay. I know why you are laughing, but okay. Why were you laughing? Yeah. Okay. That's okay. And I have been teaching for 20 years. So yeah, I don't know what I said. I don't remember. Okay. I can't go back. I will see there. Okay. So this you can prove by writing it like that and then grouping it out, and this is easy. Okay. This is easy. Okay. What this means, and this means that p of minus infinity b minus p of minus infinity a. Similarly, that you can write it and it's clear. It's easy to write. I don't want to write it. So these things will imply, I'm not proving it. Okay, this will imply for any two reasonable set, probability of x in A, y in B, okay, will imply probability of x in A times probability of x in B. Okay. Y in B. It's a measurable set. For example, if it is union of intervals, these two are union of intervals, for example, then it is clear, you can prove it. If it is union, A is union of intervals, B is also union of intervals, need not be open interval. Okay, this will just mean A cross B, where A and B are open, for example, this is true. Need not be that, if it is even, okay, not for all sets, for all sets, this doesn't even make sense, right? P of x in A is not, it makes sense only for something the sigma algebra, something so that the inverse image should be sigma algebra. Okay, so we don't need this. I'm just telling you. Okay, but if it is union of countable union of intervals, not general union of interval, A is countable union of interval, B is countable union of interval, then you can write it as interval for disjoint interval. Any interval you can, any union of interval you can write it as countable union. Any countable union of interval you can write it as countable union of disjoint interval. It's possible to write. Okay, once you do this, you just take out the corresponding sum and then write the product, group it, and then you get this. Okay, so this is true in general, but we will mostly not use it. What is the other implication? Of course, you just have to, that is for particular set. This is more general, right? We are defining this is for a particular set. If this statement is true. Of course, I'm saying, because A and B are just particular sets, no? Here the set is minus infinity x and minus. This is for all sets. This is more general than the definition. This definition implies something much more. Actually, this should be the definition of independence. This is the definition of independence in general. When you do measure theory or something, this will be the definition of independence. Okay, for any two sets, this is true. But then we don't handle it. Not any two sets, any two measurable sets, any two reasonable sets. When it is independent, definition, when I say definition for what? Definition of independence is this for in general. For us, we are just taking these two sets, that's all. But it is enough, these two sets, it is enough. From that we can prove for any set, any measurable set. What is the conclusion? Our definition of independence is this. From this, that will follow. Okay? But that is actually usually the definition. What is the other way? If that is true for everything, it will be true for this also. Okay. Of course, singletons are singleton is an interval. Of course, there is no difference because for discrete we can say x equal to something equal to we use. Here we equal to the probability will be 0. We cannot use it. So that's why we are using it. Okay. So we also have that this is equal to this. Okay. This is just the remark. Okay. X, Y are independent. Okay. Then fx x times fx y y, okay, is the density function. Is a density function I am writing because there may be more than one density function. You can change in a small set, measure 0 set or whatever, countable set or finite set or something. You get a new function. So this is the density function for this xy. On the other hand, if fxy at xy equal to f of x, f of y, then x and y are independent. This is clear, no? I don't have to prove it. Shall I say it orally? If x and y are independent, then this is true. Capital Fxy is this product. That will mean you have the integral where you have the small f of x, f of y, fx, fy. That means that is the density. That's what it means. I'm just saying if x, y are independent, then the distribution function, capital F, is multiplicative. That means that within the integral, you have those two things. So that means this is the density for that. That's what it means to be density. On the other hand, if this is density, okay, then the capital Fxy, whatever, that is just the double integral of this function, but the integral will separate because they are multiplicative. It will be product of two integrals, okay, two numbers which are actually integral, okay. So it's clear. Okay, there is nothing to prove with this. Okay. Okay. We have saw some examples. We saw some example of this. You take 0, 1 cross 0, 1, so whatever. You take uniform, I mean, the identically equal to 1. F is identically equal to 1. Then this becomes product of the density is just the product of this, and this is product. I mean, if two random variables x, y has this as your density, then it's true. So second, this example where this a equal to all those xy such that x plus y less than or equal to 1. Okay. Then you have this fxy, just right, f of xy equal to 2, right? 2 was the just the number 2, constant function 2. Okay. You have take this area A, fx equal to d, if xy is, we saw this in A and xy is in A complement, it is 0. Okay. This function is a density function, and this is the uniform density function over this. This just gave the area divided by half. Half is the area of this. We have to divide it by this. We have already seen. Then we will see that fx at x, we computed it. This is equal to what? 1 minus x, right? 1 minus x, right? Otherwise 0. Okay, and I mean it is 0 otherwise. Similarly, fy is 1 minus y. Okay, if you multiply those two things, you don't get 2. So these are not independent. We went through some other reasoning to say that they are independent in the last class. Yeah, they are not independent. We took some set and then, I mean, you take greater than or equal to half. I mean, this is great. Yeah, I mean, it is this line, right? It is this thing. You take the area, this, that will be 0. But then that is not the product of those two things. This will have a positive probability, this will have a positive probability, but that's not the product. So it's clear. Okay, these are not independent. You can have other example, same uniform example. This is just to, what is it? You can take the disk you want. A equal to, example 3, A equal to all those xy, x at x square plus y square is less than or equal to r square, some r. Okay. Then you can define xy equal to 1 by pi r square if xy is in equal to 0 if y is in a complete. Okay. Okay. Then if you compute fx at x, what do you have to do? You have to integrate it between, if you have to integrate minus infinity to infinity fxy dy, right? But then this will be between minus r square minus x square. Right? This is just this. You have to integrate between minus infinity to infinity. But then this will just the integration between this thing, f of xy dy. Okay, so that is just 2 of r square minus x square. That is just 1 pi r square divided by pi r. Okay, this is the density. Again, this is not. Okay, so the easiest example is n-dimensional standard Gaussian. Okay. Or 2-dimensional if you want. 2-dimensional I will write first. N-dimensional standard Gaussian. Gaussian is normal Gaussian or same thing. Gaussian is the mathematician and probabilist or statistician. Okay, whoever. So it's a name. Gaussian is a name. It's just named after him. And you see physics also, his name everywhere. Yeah, it's normal random variable. So that is just e power 1 by 2 pi. This is for two dimension I'm writing first, e power minus x square plus y square divided by 2. Okay. This is equal to 1 by square root of 2 pi e power minus x square by 2 times 1 by square root of 2 pi e power minus y square by 2. Okay. So this is just product of these two variables. So this is just a, I mean, if xy follows this, xy is, if x and y follows together, joint distribution of x and y is this, and the joint distribution of x is this, marginal distribution of x is this, distribution of y is this. So if you integrate it, you will get this. So they are actually, I mean, you can integrate it with respect to y, and you have to use the fact that e power minus x square by 2 equal to square root of 2 pi. So use the fact, you will get, you integrate this with respect to y. Okay, then use this fact, maybe y here. Okay, you use this fact, then you will get this. If you integrate with respect to x, I mean, how will you get the distribution of x? This is the joint distribution of x and y. You have two random variables, so that the joint distribution is this. To get the distribution of x, you have to integrate with respect to y. To get the distribution of y, you have to integrate with respect to x. If you integrate this with respect to y, okay, and use the fact that this is equal to this, then you get the distribution is this. You have to use this fact. Similarly, use the other fact to get that. Okay, so this is a joint distribution of two independent random variables. Okay, let us see an example 5. So this I don't know the constant. Let's compute this constant f of xy. Generally, we will call something as a density function if it is positive and this integral over the whole thing is 1. Okay, fxy equal to some c times e power minus x square minus xy plus y square. What's the problem? By 2. Okay, we want to find the C. Okay. So this is of course greater than 0 if C is greater than 0. So C should be greater than 0. It should be greater than 0. So C should be greater than 0. Greater than, okay, for it to be density function. C is 0, then it's not a density function. Now the next condition is it should be integrate to 1. That is integral over minus infinity to infinity minus infinity. I mean, we want to find the C. For that, I'm using this fact. Okay, f of xy dx dy equal to 1. You want to find C. Okay, so you have to find the integral of that, and 1 by that will be C. Okay, I mean, you want to find the integral of this function. You have to integrate it, and then it should be 1 by that is C. I will not do this. How do one do that? How do one does that? Integral minus infinity to infinity. You want to find this. Okay, e power minus x square minus xy plus y square divided by 2. You first write that as x square x minus y by 2 whole square plus y square by 4, right? Correct? Is that right? This is equal to this. Correct? This is right, no? Okay, I haven't made a mistake in 8th standard book. Hoyle Portstone, there's a mistake. He has, for some reason, he has put a 3 here. Huh? What? Huh? There should be 3. The y. X square, this is x square plus y square by 4 minus 2 into xy by 2. So this is just xy plus y square by 4. This is equal to that. What by 2? Oh, this whole thing by 2. Right? No. If you evaluate, this is x square. This is y square by 4 minus xy. Y square by 4. Oh, it's only y square by 4. Ah, okay. Going in the 3. Okay, good. Okay, that's right. Okay, yeah, I made a mistake. Okay. Okay. So I erase it because you are going to do this. Okay. 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 This is okay. Now, when you write like that and do the change of variable, then you use this fact. All of you hope remember Gaussian density. You remember, everyone remembers, I believe. You use that, or you can use the fact that e power minus x square by 2 dx equal to square root of pi, 2 pi. Then you get this. Okay. From this, first you integrate it, you will get a function of x. Then you integrate it with respect to, if you integrate with respect to y or x, depending upon you make this square. Then you get a function of x or y. Then you integrate with respect to that. You get a constant finally. 1 by that is what we. Okay, that's number 1. So now I define what is called covariance. I will give one more, okay, definition. Okay, covariance of xy. What is covariance of xy? This is just e of x minus ex times y minus ey. Okay, which is same as e of xy minus e of x times e of y. Okay. We have already defined it. Same thing, no? We have defined for discrete. There is no difference. Okay, that is what is this. But then covariance of xy by whatever we have done, this is equal to integral of xy f of xy minus, of course, integral of x f of x dx, integral of y f of y dy. Okay. Have we written anywhere Gaussian? I will erase. I mean, we have some time. I will give you the quiz of computing this. It's not compulsory. You can, I will give you the quiz to compute these two things for this function. Let me write it here. I will repeat it here. Okay. Let xy, joint distribution of xy distribution is e power minus x square plus minus xy plus y square divided by 2. Okay. C times this. Compute C and covariance of xy. Okay. You don't need to take it. I mean, this will not affect your exam. This will only an inside thing. If you want to do, it will, okay, it's up to you. Okay. Don't send message anyway, I will lock it. I will, don't send message to anyone. It's doable in 15 minutes, I think. You can take paper, or if you have a paper, you can. Yeah, I'm sorry. This is going on.